objective is to design two interlocking components with a quick release for a spacesuit utility belt. This will develop a quick, reliable process for astronauts to engage and disengage their tools to increase the efficiency of a spacewalk. The quick mechanism will operate manually in microgravity, function in extremely cold weather, and covered in moon dust. The male end will interlock with the female end, and a safety latch has been added for no accidental discharge. Here is a picture of the old method of how astronauts would disengage and engage their tools. NASA has implemented the Artemis program in 3 stages. They return astronauts back to the moon in October 2024. The first female astronaut and next man will be landing on the South Pole region of the moon, where they will be mining for ice. Moon dust is highly problematic for astronauts' equipment. Moon dust has angular geometries and sharp edges due to the moon being in a vacuum. Moon dust has a collection of positive charges due to the photo emissions and a collection of negative charges because the transmission of electrons goes to a lower energy stage. Lunar dust also becomes ferromagnetic because of the significant presence of iron, which can be problematic to the astronauts' equipment if given off a magnetic field. The team set off with 3 initial materials: aluminum 6061 for its excellent machinability and formability, good resistance to weathering, reasonable strength, and low weight; stainless steel for its high ductility, high strength, and good resistance to extreme temperatures; and Teflon for its neutrally charged surface, low friction, and low weight.
I want to take a moment to talk about our specifications. When we came into this challenge, we were given 14 requirements that had to be met. We broke those into 16 specifications in quantitative, qualitative, and for safety. Mike already hit on the materials on the quantitative section, but I want to hit on 3 more points: the assembly volume, the assembly weight, and the load capacity. These are all crucial for any NASA mission because the saying goes, to send 1 pound into space costs $10,000. So we wanted to make our project as small as possible, but as efficient as possible. Let's take a look at the qualitative section. The qualitative section is a little bit more intangible. We want to work on making our device as user-friendly as possible. So if the device is on your hip, you can look any way you want to and use the tool, but also only use it with one hand, leaving one hand free to do whatever you need to do. Now let's take a look at the most crucial section, safety. We were told to minimize risk as much as possible. Our team took that a step further and we eliminated any risk possible. We have no sharp edges on our projects, no pinch points on our project, and we tried with so many different gloves to get our fingers stuck in our device, and it never happened, making our device one of the safest ones out there. Now let's take a look at what this device looks like in the final prototype, cycling on the screen. Now this is the assembly and disassembly of the device. It breaks down into 3 major parts: our female end, which goes to on your hip, the male end, which attaches to any tool out there, and then the roller catch and safety lock, which joins the 2 together. That roller catch holds the piece in place no matter what the astronaut is doing. Are they jumping around? Have they fallen down? Has lunar dust got into it? It doesn't matter. The safety latch and the roller catch will keep it together.
For the manufacturing process, our team initially started off by printing the design with a 3D printer. Our team performed a total of 5 prints of the entire assembly, and design improvements were added after each print. We wanted to see how we can improve on the existing design and also confirm functionality of the system. As well, we wanted to ensure proper fitting of moving elements. If there was ever any weakness with our design, we went back and redesigned those parts. Here you can see the picture of our final PLA prototype. We have the male end, female housing, and the entire assembly. After ensuring the 3D printing version of the design was good and everything worked properly, we went to a machine shop, and with the help of the staff there, we were able to manufacture our final prototype. Our final prototype was manufactured in Abel's Machining Services located in Stafford, Texas. Our team was very much involved with every step of the manufacturing process. The female housing is CNC machined and is made out of aluminum 6061. The male end is also made out of aluminum 6061. The security lock and the roller catch bottom plate were made out of Teflon. Here you can see the picture of all the components of our design.
So as Monica mentioned earlier, we had 14 requirements we had to meet, and two of the easiest requirements to test for were the weight and dimensions of the prototype. After construction of the prototype, we weighed it and found it to be about 0.56 pounds, which is far under the 2-pound requirement. Also, the device fit within the 4-inch by 4-inch by 3-inch volume. A large part of what we were testing for was the manual operation of our device. About 5 of the requirements rolled into one, those being you need to be able to use it with a thick glove, such as a ski glove or a lineman glove. You had to be able to use it with one hand, out of line of sight, and it had to be easy to operate. On the screen, you can see us doing our moonwalk test with a 15-pound kettlebell attached to our quick release system. There was no deformation, no damaging of the system in any way, and it was able to hold the 15-pound weight with ease. One of the most important tests we performed was the Lunar dust simulant test. We wanted to make sure our device was operational in a multitude of grain sizes. You can see the 4 grain sizes we chose from 4070 mesh down to 2500 mesh, which is a very fine clay-like powder. We submerged the device in each of these and cycled it 10 times without any difficulty, and then we mixed them all into a slurry and tried to combine them all into a more realistic composition of grains, and found that the device operated nominally. After meeting our 14 requirements, we wanted to go a step further and make the improvements we thought would help our final mechanism. On the screen, you can see on the left the double roller catch, and on the right the male end rod and plate. These are the pieces that are going to be under the most stress and strain, so we wanted them to be easily replaceable. The roller catch comes straight out of the female end, and the rod unscrews from the plate so that you don't have to replace the entire thing in the event of damage. For our future work and improvements on our project, one of the first steps we'd like to do is anodize the aluminum in our school colors. Go Patriots. Another future work step would be to add a spring washer to the male end rod. What this would do is keep the tension between the male end rod and the male end plate, making it less likely for them to actually separate. Another improvement would be to create a tap hole through the female end all the way. We realized that it might potentially trap gases where the screws go in the cover plate. So one of the fixes would be to drill a hole all the way through so no gases are captured.
One of the other elements to our project is the need to quantify the total cost of the prototype and production. And so early on in the semester, we recognized that we could implement a variety of techniques, from 3D printing in alloy to classical machining and CNC machining techniques. We went ahead and selected CNC machining because of its affordability and overall turnaround time. The team had budgeted roughly $1,000 for the prototype. That includes the overall cost of materials as well as labor hours. As is pretty evident, with COVID-19, it was very difficult to access machining facilities and equipment, and so a portion of this project had to be outsourced to a local machining shop out of Stafford, Texas. Though the team was fully involved and immersed during the whole manufacturing process. The end cost of the prototype came out to be $875. That cost is inclusive of both materials and labor hours. And in typical engineering projects, it is not out of the world, right, to see a labor hour charge of roughly $80 per hour. And so this is what we had to absorb in order to deliver on the project expectations. I'd like to take a moment to also acknowledge all of the support that we had throughout the course of the last 2 semesters. First, our professor, Al-Sal Shalash, who is our advisor, and then some of the staff from University of Texas at Tyler, including Dr. Bearcat, the department chair for mechanical engineering, and Dr. Andres Garcia, who is the director of the Houston Engineering Center. Without their support, all of the hard work that the team was able to showcase could have not been possible. Thank you, and we'll open the presentation for questions.